This video is on a hypothesis test for population proportion. But before we can get into the concept of population or a test for population proportion, an important definition is the p-value. P-value is simply the probability of observing a sample statistic as extreme or more extreme than one observed under the assumption that the null statement is true. Now that might seem like a very complicated statement, but a simple case would be, let's say we have a null that p is equal to 0.5 and the alternative is p greater than 0.5. We collect a sample, we perform a test, and we end up getting the p-value. So once we have the p-value, we know alpha which is the level of significance chosen by the researcher. In addition, one has to realize that alpha is the probability of type 1 error, which is the probability of rejecting the null when the null is true. We want this error to be really small. So p-value pretty much tells us it is the conditional probability based on current evidence toward the null. Key words here would be conditional probability, and based on current evidence. Given the evidence, given the assumption, and under the null assumption, what are the chances that the null is likely to be true? In other words, going back to our example where we had p equals 0.5 against p greater than 0.5, suppose the p-value happened to be let's say the p-value is 0.001. So this is the conditional probability based on the data that we collected under the null that we found evidence toward the null. So this tells us there is 0.1% probabilistic support toward the null, which would imply that we have to reject the null statement because the data is only giving us 0.1% probabilistic support. Therefore, we have to reject the null. So how would we go about conducting a test? There are a few steps involved, and specifically we are going to talk about a hypothesis test for population proportion. So the very first step is to make the definition. So we're going to make an assumption for the proportion of the population. So someone would make a claim about the population proportion, and we are going to start with that initial value. So in this example, that initial value was 0.5. So that is P0. Depending on the alternative statement, which is the claim, we are going to either choose a left-tailed test, a right-tailed test, or a two-tailed test. If we read the claim statement, we are claiming that the population proportion is greater than P0, which is 0.5, so we will pick a right-tailed test. Once we define, the next step would be to give a level of significance against which we are going to conduct this test. So keep in mind, alpha is the type 1 error. So we are fixing the type 1 error. For example, if we choose alpha equals 0.05, the maximum amount of type 1 error, to be specific, the probability of type 1 error we can tolerate is 0.05 or 5%. So that is the cutoff, and if we can't achieve that probability, in other words, if that probability ends up being 15%, then we don't find evidence toward the alternative and we do not reject the null. So there are two approaches in conducting a hypothesis test for a population proportion. One is what we call the classical approach, where we find a test statistic given by this formula and the goal is to compare the test statistic to a critical value, which depends on alpha, the level of significance. In other words, the maximum probability of type 1 error that we are willing to tolerate. So I am going to show you how to find this test statistic using a calculator, but in terms of the formula, P hat would be the sample proportion, P naught is the claimed value or the null value, and we simply have to compare the test statistic to the critical value, which depends on the value of alpha, the level of significance, and that is what we call the classical approach. So the approach depends on the type which is why identifying the correct test is crucial in performing a hypothesis test. So here is a case where we have a two-tailed test. So if we have a two-tailed test, we would have two critical values. One on the right tail and one on the left tail. So the region here is what we call the critical region on the real number line. The probability corresponding to that would be alpha over 2. Why is that? Let's say alpha is 0.05. Then, since this is a two-tailed test, we are going to allot an area of alpha over 2, which is 0.05 over 2, we get 0.025. In a similar manner, we are going to allot an area of alpha over 2, which is 0.05 over 2, we get 0.025. Why do we have to set up this way? If we set up this way, we end up having 95% in the middle. In terms of alpha, that would simply be 100 minus alpha percent. We denote the critical values as negative z sub alpha over 2, and it is alpha over 2 here because the area is alpha over 2, and it's alpha over 2 there because the area above the critical value is alpha over 2. We have a negative here because it's on the left hand side of 0, and keep in mind the middle value right here is 0 and on the other side we have a positive value because it is a positive critical value. So to be specific, we can call that the negative critical value, and we could call that the positive critical value. So why do we have to use the letter Z right here? Why Z indeed? So that denotes, the letter Z denotes, or it implies that we have to use a standard normal distribution, which simply is a normal distribution with mean equals 0 and standard deviation equals 1. So what if the test happens to be a left-tailed test? If it is a left-tailed test, the rejection region or the critical region will be on the left. So 0 would be right in the middle, and in this case we would only have a negative critical value. So if you notice, you would see alpha and not alpha over 2. The reason being, in the previous case we had alpha over 2 because we have to have two critical regions, one on the left hand side, one on the right hand side, and the probability when we add from both sides must equal the value that we set for alpha. But in this case, since it is a left-tailed test, there is only one critical region, so all of that area would correspond to alpha. So if we set alpha equals 5%, all of 5% would be right here, which would imply 95% will be on the other side. The third case, of course, is the right-tailed test, and naturally the rejection or critical region will be on the right tail, and we would only have a positive critical value, no negative business here. And if you notice, again, alpha is what we have. The reason being we don't have to divide the alpha, we are loading the entire area alpha to the right tail. So what does the critical value approach state? Now, there is a picture, of course, table here, but I'm going to draw some pictures to explain this. So, key thing to notice is Z sub 0, which is the test statistic. Negative Z sub alpha over 2 would be the left critical value, and positive Z sub alpha over 2 would be the right critical value. So we use the data to find the test statistic. It is important. Then we use that test statistic to obtain a conclusion. So how do we go about doing this? So 0 is right in the middle, and we are going to find two numbers. If you look on the real number line for a two-tailed test, we have negative Z sub alpha over 2 and positive Z sub alpha over 2. So let's go ahead and draw those two, or place those 2 points. And what we have there is the rejection region. So if the test statistic falls here or there, then we reject the null. That is with a two-tailed test. If we have a left-tailed test, we have only one rejection region, and it is on the left-hand side. So 0, and that is our null, and that is the left-hand side. And if the test statistic falls over here, then we reject the null. And of course the last case is the right-tailed test, and right-tailed test would have a rejection region only on the right tail. So 0 is right there, and the rejection region is right over there. So if the test statistic falls right there, then we reject the null. When I say false on some side, I mean on the real number line. You have to keep that in mind. So that number corresponds to some number on the real number line. The second approach is the p-value approach, and it is the most commonly used approach in practice. It also depends on the value of the test statistic, and the formula for that is this, and I'm going to show you how to find this using the calculator, and that only applies to a test for population proportion. So what does the p-value approach tell us, or how does the p-value approach work? Of course, we have to find the p-value. So for a two-tailed test, it is simply the area above the absolute value of the test statistic multiplied by 2. So in words, this would simply mean the area above the absolute value of the test statistic multiplied by 2. So again, the test statistic is that value and that value over there. And you can see that we take the absolute value. And I'm going to show you how to find the p-value using a calculator as well. It's coming ahead. So for a left-tailed test, the p-value is simply the area below the test statistic and or to the left of the test statistic. So keep in mind, when I say area, we mean to say the probability under the density curve. So we typically, or we will have to make use of a CDF to find the p-value. With the right-tailed test, the p-value has to be on the right-hand side, so the p-value is right here. So it corresponds to the area above the test statistic, or some would like to call it as the area to the right of the test statistic, which is looks like I lost it. And when we mean area, again, we mean to say the area under the density curve, which is a cumulative probability and we will have to make use of a CDF. So how do we come to a conclusion with a p-value approach? If we go back to the critical value approach, we looked at where the test statistic falls. If it falls on the left-hand side, with the left-tailed test, we reject the null and so forth. But when it comes to the p-value approach, we simply compare the p-value to the value of alpha, which simply states reject the null hypothesis. So, for example, suppose a statistical test so alpha is simply the maximum probability of type 1 error that we are willing to tolerate, and p-value comes from the test that we performed. So what would the conclusion be? In this case, we would reject the null because p-value is less than alpha. So p-value is 0.001 and alpha is 0.05, and clearly p-value is less than alpha. So once we establish either using the critical value or classical approach, or using the p-value approach, we come to a conclusion. What is that conclusion? Keep in mind, it is going to be only one of two things. Either we do not reject null, or we reject null. It's always one of the two. So we never say we accept the null. We either reject the null or we do not reject the null. So with the classical approach, if the test statistic falls in the rejection region, we would reject the null. With the p-value approach, if the p-value is less than alpha, we reject the null. So with classical, the test statistic has to fall in the rejection region for us to reject the null. With the p-value approach, to reject, we must have p-value less than alpha. So here is an example where in 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately and fairly. In a 2007 poll of 1,010 adults nationwide, 525 stated they did not trust the media. So we have to use a 0.05 level of significance to determine if there is support toward the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997. So we have to break the question into pieces. So first, let's identify the population proportion. P is simply the proportion of Americans who do not trust the media. So the claim here is that this proportion has gone up since 1997. And in 1997, that value was 0.46. So it has increased since 1997. So the claim here is that the proportion has gone up, so it is greater than 0.46. So the very first step is to come up with the definition. The null is P equals 0.46. The alternative is P greater than 0.46. Look at the alternative. It has a greater than sign, which would imply a right side. The moment we recognize that there's a right side test, things that need to keep in mind is that the rejection region is on the right side. Critical value is positive. The p-value is the error above or to the right of the test. All of this will come to your mind right away. So the second step is to look at the value of alpha, and alpha is 0.05, and that would be the maximum probability of type 1 error that can be tolerated or permitted in this test. The next step is to find the test statistic. Of course, one can go and use the formula, which is Z naught equals P hat minus P naught divided by square root of P naught times 1 minus P naught divided by N. We can circumvent this and use the calculator instead. So press start, go over to tests, and we are going to perform a one proportion test. So I'm going to select number 5. P naught is what was claimed. It is 0.46. And the sample from 2007 tells us they observed 1,010 adults and 525 stated they did not trust the media. So X is 525 and N is 1010. So the sample proportion would simply be X over N, and here let's fill in the stuff. 525, 1010, P0, and B calculate. So the sample proportion is P hat, and it is 0.5198. So the question here is that value 51.98%, which is definitely greater than 46%. Is that value statistically significant for us to conclude that the proportion of people who do not trust the media has gone up from 46% since 1997? So let's do both approaches here. The classical first. The rejection region is only on the right hand side. And alpha is 0.05. So I'm going to plug in 0.05. And that area is equal to alpha, so we have 0.05. Keep in mind the critical value is a percentile, and we know that percentiles are computed using inverse norm function. And we have to enter the area below z sub alpha, which is that point right there. So if the area to the right or above z sub alpha is 0.05, the area below is 0.95. So I'm going to type in 0.95, 0 and 1. Which would give us 1.645. So where does the test statistic fall? We have to go back to our test. And what values did we have? We have z, which is z sub 0, that is 3.819. The second p that we see is the p-value, so that is 6.85 times 10 raised to negative 5, which is 0.00006. So where does the test statistic fall? If you look at the real number line that we have over here, 1.645 is right there, that point. So 3.813 is right there. So the test statistic clearly falls in the rejection region. In other words, we have to reject the null. The next approach is the p-value approach. Here we simply ask one question. Is p-value less than alpha? If it is, then we will reject the null. So p-value in our case is 0.00000675 and alpha is 0.5, so we will reject the null. And if you look at it, the conclusion is the same between the classical approach and the p-value approach. It has to be. So what I've done here I've copied the same example, but I'm going to make a subtle change so you can understand the differences between the three tests. So here is the first case. It is the same problem, but I'm going to change the wording. Instead of increased, I'm going to simply say changed. Now, what does change mean? Change simply means it could have gone up from 46% or it could have gone down from 46%. So what type of test should we perform here? Here it would be a two-tailed test. So what is the definition? The definition is p equals 0.5. The alternative is p not equal to 0.5. And that is the claim. The value of alpha does not change, so that is 0.05. The moment you recognize that this is a two-tailed test, the things that have to come to mind are the rejection region is on both sides or both tails. The area of the rejection region is alpha over 2. There are two critical values, one on the right and one on the left. So I changed the definition, but I didn't change the data. So everything that we had previously will still be the same because I did not change the data. So x is 525, n is 1010, p hat is 0.5198. So if we go about doing the classical approach, there has to be two critical values, one on the right hand side, the other on the left hand side. But mind you, the area under the curve here is alpha over 2. The area under the curve there is alpha over 2, which in this problem is 0.05 over 2. We get 0.025, which would be the same on the other side. Sorry. So that number on the left hand side would be negative z sub alpha over 2 or negative z sub 0.025, and on the right it is z sub alpha over 2 or z sub 0.025. So how do we find the critical values? We make use of inverse norm. We can either pick the one on the left hand side or one on the right hand side. But keep in mind, inverse norm requires the area below, and the area below that point here under the density curve is 0.05. And that gives me a value, sorry, it's 0.025. A value of negative 1.96. If that value below 0 is negative 1.96, naturally that is going to be positive 1.96. So the rejection region is right over there and there. So how do we find the conclusion? We know z sub 0 from earlier because I did not change the data, so was 3.819. So 3.819 is going to fall somewhere over there. So the test statistic falls in the rejection region, therefore we reject the null. Now we could do the p-value approach, so let's go back to start over to tests, number 5, and everything stays the same except the fourth line. Here the definition of the test changed, so we have to go from greater than p0 to not equal to p0, and that would give us a p-value (0.00014). So that simply that would just result in the conclusion that we reject the null because is p-value less than alpha. Alpha is 0.05. P-value is 0.00014. Certainly the question is true, so we reject the null. So what is our conclusion? The proportion of Americans who do not trust the media has changed since 1997. So in this test, we're simply concluding that it changed. We're not giving the direction if it increased or if it decreased. We're simply saying that it wasn't the same as it was in 1997. So keep in mind, this conclusion agrees with the conclusion here because we rejected the null, which would imply p is greater than 0.46, which would imply the proportion of Americans who do not trust the media is greater than 0.46. So that was our conclusion with the right-tailed test. We reject the null and say, oh, it is greater than 0.46. Well, if it is greater than 0.46 since 1997, that was the original proportion, greater than is true, which means it changed, and it changed for or changed to to a value greater than 0.46. So if the right-tailed test indicates it is greater than 0.46, it should imply that things changed, and you can see that we came to a similar conclusion that the proportion of Americans who do not trust the media has changed since 1997. A key thing to notice here is if the definition of the test changes, the p-value will certainly change. So I am going to change that statement, and instead of increased, I'm going to say decreased. Just realize the typo in the question. In the previous one, that part shouldn't be there. And in this one, it shouldn't be there. So here we are starting with the null, which is p equals 0.46, and the alternative, since 1997, that original value of 0.46 has gone down. It's decreased since 1997. So the alternative here is p less than 0.46. This would indicate a left-tailed test. Things that need to come to your mind if you determine a test is left-tailed is that the rejection region is on the left-hand side, the critical value is negative, and the p-value is the area below or to the left of the test statistic. Now we're not changing the value of alpha. We're keeping the value of alpha at 0.05. And we did not change the data, so nothing will change. So x is the same, n is the same, p hat is the same. The test statistic will also be the same. We'll do the classical approach or the critical value approach. The rejection region has to be on the left-hand side. and that value is negative z sub alpha. Why is it alpha? Because the area is alpha, which is 0.05. So we can find that critical value using inverse norm. The area below that point is 0.05. So what we are trying to find is negative z sub 0.05. So inverse norm 0.05, 0 and 1. So here the critical value is negative 1.6448. But the test statistic is right over here, 3.813. If you notice, the test statistic doesn't fall in the rejection region, therefore we do not reject null. If we use the p-value approach, keep in mind, if the definition of the test changes, naturally the p-value will change. So I'm going to change the definition to less than p naught because it's a left-tailed test. And we end up getting a p-value of 0.9993. So the question to ask is p-value less than alpha? No. P-value is 0.9993, alpha is 0.05. We said no, which would mean do not reject the null, which would imply of the two statements, we are going to not reject the null. So not rejecting the null would simply mean there is no evidence toward the alternative, which makes perfect sense. So the conclusion here is that the proportion of Americans who do not trust the media has not decreased from 0.46, and that is based on 1997 poll. So that is our conclusion. Does that make sense? If you go back and read the question, it was 46%, and we collected the data and we end up getting 51.98% in the year 2007. So by all means, the proportion has gone up. So it would be completely wrong for us to conclude that the proportion would be less than 0.46, which is the alternative. So which is why the test is telling us that the proportion of Americans who do not trust the media has not decreased from 0.46, because clearly it has changed. And how did it change? It increased from 0.46 to 0.5198. And is it statistically significant? It is, because we rejected the null in the last two problems.